Hello, everyone. So you're welcome to this lecture. We have discussed an introduction to rings. I will define what a ring is, looked at some properties, basically a theorem on multiplication. We discussed ring isomorphism and homomorphisms. So in this lecture, we want to look at subrings. We define subring. Basically in this video, and then in subsequent ones, I will look at fields and then we'll look at integral domains. Okay, so that is the plan for this lecture. So a subring, given a set R here, right, which is a ring. When I say a set R, of course, I'm talking about a set together with operations of addition and multiplication. So given a ring R here, a subset S of R is called a subring if the elements of S also form a ring under addition and multiplication. So S has to be a subset and the elements must form a ring with regards to the same operations, right, as in R. Okay, this is very similar to the definition for subgroups, right, where you have a set, you have a subset of it, and then the elements must form a group, and you call it a subgroup. So it's very similar. Here's a typical example of that, right? If you take the set of integers, these form a ring under addition and multiplication, right? Ordinary addition and multiplication. Well, the set of even integers, 2z here, right? Of course, it's a subset of the set of integers, and this form is a ring, and therefore it is a subring. So the set of even integers form a subring under ordinary addition and multiplication as well. Well, you can test the axioms, right? First, you have to show that 2z is an abelian group, right? Then you have to show that multiplication is associative, and then you show that the left and right distributive laws hold, basically. So once you've shown that, you have shown that this is a ring, and since it's a subset of z, then it is a subring of z. Okay, so that is it. And then here's an interesting one. We've come across this set before, the set S with elements 0, 2, and 4. This form a subring, right, of the ring Z6, that is this integers modulo 6. Okay, of course, integers modulo 6 is has elements, 0 to 5, right? So okay, so I still have my thing here. Z6 here has elements 0, 1, 2, 3, 4, and 5. S here has elements 0, 2, and 4. Okay, good. Now to show that, this is a ring, right? You need to first show that it is an abelian group. In other words, well, it's a group with regards to addition. So you have to show that there's associativity with regards to addition. You have to show that there is an additive identity element. Of course, that is 0, so that is easy. You have to show that there is additive inverse for every element. Okay, that is where it's tricky because for the integers modulo 6 or modulo n, you don't have negative numbers, right? Just positive numbers here. So how do you get the additive inverses? Well, the additive inverse is any element, right? When added to an element gives you the identity. All right, so that will be the element that gives you the additive inverse. So that's what I'm demonstrating here. Okay, so to do that, you can use this table, right? So this is plus. In some text, they will put a 6 under the plus to show that it's not ordinary addition, right? It's addition modulo 6. So 0 plus 0 is 0, 0 plus 2 is 2, and then 4 is 4, 2 plus 0 is 2, 2 plus 2 is 4, 2 plus 4 is 6. Modulo 6 will give you 0, right? 4 and 0 is 4, 4 and 2 will give you 0, and then 4 and 4, that's 8, and modulo 6, that's 2. Okay, so you see that 0 plus 0 gives you 0. Okay, so 0 here, right? 0 will be the additive inverse of 0. And you see that 2 and 4, right? 2, right? 2 plus 4 will give you a 0. Okay, so which means that 2 and 4 here is the additive inverse of 2. Also, you see that 4 plus 2 is equal to 0. Okay, So of course, what this means is that under this set here, 2, if you like, 2 is the same as -4, right? And then if you like, 4 is the same as -2. Okay. So or if you like, -2 under this set here will be 4, and -4 under this set will be 2. So even though there are no negative numbers in here, right, you can determine the additive inverses for each element. Okay. And then you can use that to actually show that this is an abelian group. You can show that there's multiplicative associativity, and you can show that the distributive laws hold, and therefore it's a ring. And since it is a subset of the set of integers modulo 6, it forms a subring. Okay, good. So that is how you show that, you know, these finite sets form a subring. So take a look at it, and then convince yourself. Okay, good. Now we'll move on to tests for subrings. Okay, so in other words, instead of going through all the axioms for a ring, we'll look at two theorems that will actually help you to directly determine if a given set is a subring. Okay, instead of going through all the axioms. So you just prove one theorem and it helps you to do that. So the first one is this. Let R here be a ring and let S be a subset of R. Then S is a subring of R if and only if the following two conditions are satisfied. The first one is that S with regards to addition is a subgroup of R with regards to addition, okay, or under addition. And then the second one is that S has to be closed under multiplication. That is, if I take any two elements in S and multiply them, the result is in S, okay? So how do you prove that? Well, it's an if and only if statement here, right? So first you assume that S is a subring, okay? It is a subset, this is given to us, and then we assume it's a subring, and then if it's a subring, then we prove these two. And then conversely, we assume that these two conditions are satisfied, and then we prove that S is a subring, okay? So the first part is straightforward actually, right? If we assume that S is a subring, then of course it's a ring. So it satisfies all the conditions of a ring. That's what it means, right? So if you assume that S is a subring, then of course it shows that S is an abelian group with regards to addition, okay? If it's an abelian group and R here is an abelian group, but S is a subset of R, then of course S here forms a subgroup of R, okay? So that is a proof for the first part, that's easy. And if S is a subring, then of course it is closed, right, with regards to addition and multiplication. Therefore, multiplication must be closed, right? Look at closure in our very first lecture or second lecture, right? Closure means that under multiplication means if I take any two elements and multiply them, the result is also in S, okay? Since S is a subring, multiplication is closed under S, and therefore condition 2 also holds. So I and II automatically hold if we assume that S is a subring. Good. Then we prove the converse, right? The converse is to show that, is to suppose, right? Is to suppose that I and II are true, okay? And if they are true, right? If I is true and S is true, then we need to show that S is a subring, okay? Now to show that S is a subring, of course, then you have to show or employ the axioms for a ring to show that S is a subring, right? That is basically how you do that. So basically, you want to show that suppose these two conditions are satisfied, then we want to show that S plus here, right, is abelian, right, an abelian group. Okay, once we have shown that, we want to show that multiplication is associative, right? Those are the axioms: associative, Then thirdly, we want to show that the distributive laws hold, right? The left and right distributive laws hold, okay? So if we assume these two conditions are satisfied, I and II are satisfied, then you want to prove this. Once this is proved, then you have shown that S is a subring, okay? And that is really straightforward. The first, these and this are straightforward because if you assume that these two conditions are satisfied, well, and of course we know S is a subset of R. Okay, so all the elements in S are also elements of R, but all the elements in R obey the multiplicative associativity law, right? And therefore, the elements in S must also obey multiplicative associativity. Okay, so that is true for S. Also, all the elements in R obey the distributive laws, and therefore, all the elements in S must also obey the distributive laws because S is a subset of R. Okay, so these ones are given, really, they are straightforward. Maybe the one you have to think a bit about is this one, to show that S here is an abelian group. Well, condition one shows that it is a subgroup of R with regards to addition, therefore it is a group. So you just have to show that it is abelian, in other words, it's commutative with regards to addition. Okay, well, that is easy again because S is a subset of R and all the elements in R are commutative with regards to addition. Therefore, all the elements in S must be commutative with regards to addition. And therefore, S is not just a group, it's an abelian group, right? With regards to addition. And so 1, 2, 3 hold. Therefore, S is a subring. Okay. So I actually have the proof. I have the proof here, right? So actually here it is just stated straight away, right? Without much of the explanations I've given here. So we have, let me do this. Let me blow it up a bit. So we have the proof is here, right? Let R be a ring and let S be a subset that is given to us in the theorem. Suppose that S is a subring. So that's the first part. We suppose S is a subring, then of course the first two conditions hold because of the reasons I've given, right? They hold because, I mean, S is a subset, therefore it's a subgroup, right? All the elements in S must obey the rules in there. Conversely, if you suppose the two conditions 1 and 2 hold, then addition and multiplication, right, form binary operations. That's what this means. If this is true and that is true, then of course addition is a binary operation under S, and multiplication is also a binary operation under S. Okay. And this guy here is an abelian group. I've explained that, right? It is first of all, it is a subgroup, therefore it's a group. To show that it's abelian, we'll show that it's commutative, and we use the fact that all the elements in S are elements in R, and the elements in R obey commutativity, therefore the elements in S also obey the commutativity with regards to addition. Okay. Associativity and distributivity also hold, all right, for all the elements in R because R is a ring, of course, and therefore they must hold for S because S is a subset of R, and all the elements in S are also elements of R. So that is really the proof. Okay, so that's straightforward. So to test that something, a structure or a set, if you like, is a subring, you could just use these two tests. First of all, if you can show that it under addition is a subgroup of this, and you can show that multiplication as closed, then you can just conclude that the set is a subring. Okay. Here's another one. This is probably most popular, right? You'll see this mostly in most books and most materials, textbooks and stuff. So to show that, okay, let me just read the theorem and then we can explain a bit. If R here is a ring and S here is a non-empty subset of R, then S is a subring of R if and only if the following two conditions hold, right? if R1 and R2 are in S, then if you like, subtraction is closed, right? R1 minus R2 must be in S, and multiplication is closed as well. If I pick R1 and R2 in S, then the product, okay, is also in S. So once again, you could use this when you're given a set and you want to show that it's a subring. You could just test these two conditions, right? Take two elements in the set, find the difference between them, and show that the difference is actually also an element in S, the product is in S, and then from these two conditions, you can just conclude that it's a subring without going through all the individual axioms, okay, for a ring. So try and prove this. Okay, it's straightforward actually. So you could well, to prove the first one is easy. That is really why it is a corollary to the other theorem, right? So you could use this theorem here, this one, to help you to prove it. Okay. First, assume that S is a subring, and then show that these conditions are satisfied, right? Which is easy to do. Remember that under groups, this guy here, let me bring up my thing. So under groups, note that this R minus R1 minus R2, right, is the same as R1 plus negative R2, right? So you want to show that, R1 plus, the additive inverse of an element R2 here is also in S, okay? So that's what you want to show. And then you want to show that if you take two elements and multiply them, they're in S, therefore, so first suppose that S is a subring and prove these two, okay? Which is straightforward, because if S is a subring, then of course it's a ring, and therefore it's an abelian group, and all the other, conditions for a ring hold for it. And then the converse is why you have to do a little work, right? You suppose that this is true and that is true, and then from here, show that S is a subring, okay? In fact, in some texts, these two conditions are split into three conditions. They're identical to this. So the first one, you want to show that if I pick R1 and R2, then R1 plus R2 is also in S. Secondly, I want to show that multiplication is closed. R1 times R2 is in S. And then thirdly, you want to show that if R1 or R is in S, the negative of R is also, or the inverse, if you like, of R is also in S, the additive inverse, okay? Really, these are identical to these conditions, but this is the popular one, okay? So keep this in mind. If you are given a set, you want to show that it is a subring, it's enough to show that if I take any two elements and subtract them, the result is also an element of S. And if I take two elements and multiply them, the result is in S. From there, you just conclude that yes, it's a subring. So keep that in mind. Okay, good. Let's move on to something else. A few more things. Here we have, we'll look at the zero ring, basically leading us to something. We've come across the zero ring already, right? We said it's a trivial ring. And I said that it is your duty to actually go through all the axioms to satisfy yourself that the zero ring is actually a ring, right? It satisfies all the axioms. But note that if I take 0 plus 0, I get 0. If I take 0 times 0, I get 0. What that means is that 0 here is its own additive identity, right? It is also a multiplicative identity, okay, to itself. So the zero ring, in the zero ring, 0 is the multiplicative identity. At the same time, it is the additive identity. It is the only ring where that happens, okay? That's the only case where you have 0 acting as a multiplicative identity, okay? So, I mean, using theorem 11, where we show that A times some element is 0, while if A is non-zero, this will definitely show that A is equal to 0, right? So we'll be looking in the next few lessons, we'll actually want to look at elements that are not zero or rings that are not a zero ring. We want to see if elements in such a ring, right, would have additive or multiplicative identities and multiplicative inverses. Okay, so this is moving us closer and closer to what a field is. That is why we are introducing that. Okay, so keep this in mind. This is only true, right? The zero thing is only true for the zero ring. Okay, so this is what I just explained, right? We're going to discuss the existence of multiplicative inverses for non-zero elements in a ring. So if you have non-zero elements, we want to know whether those elements have multiplicative inverses or non-zero unity and all of that. Okay, good. Now, so let's define what a unit is and what a division ring is, and then we'll end the lecture there. And then I'll do another one where we'll talk about fields, okay? So a unit, I'll let R here be a ring with unity. We've come across unity already. Unity is the multiplicative identity, okay? And I mentioned that the one here is just used to denote the multiplicative identity. Sometimes it's not just the number one, right? It could be something else, right? When we looked at the subset of integers modulo 6 with elements 0, 2, and 4, remember that we said 4 was the identity element there. So this is just to denote what the unity is. Okay. So let R be a unity, a ring with unity 1, which is non-zero. An element U in R is a unit of R if it has a multiplicative inverse in R. Okay, so every element that is non-zero with a multiplicative inverse is called a unit. Okay, so don't confuse unit with unity. Unity has to do with the identity element. Okay, but the unit has to do with a multiplicative inverse. Okay, that's the difference between them. Don't know who introduced these terms. They can be confusing, but keep that in mind. The unit is different from unity. Unity has to do with the identity element, multiplicative identity, whilst a unit is an element, a non-zero element that has a multiplicative inverse. Okay, so if A is an element in R, well, if I multiply the units, right, by A or A by the unit, I get back my unity. Okay, I get back the unity in the set. Okay, that's a multiplicative identity. So that is called a unit. Good. Now, what is a division ring? A division ring or a skew field? Okay. A ring R is called a division ring if R has unity that is non-zero. Okay, and every non-zero element of R is a unit. Okay. What that means is that every non-zero element has a multiplicative inverse. Okay, so keep these terms in mind, they're very important. Okay, so that will be called a division ring if I have a ring that has non-zero unity, and if I pick any non-zero element in that set in the ring, it has a multiplicative inverse, then it is called a division ring. Okay, another way that you could describe a division ring is to say that, you know, if you take the set R without 0, then it forms a group under multiplication, right? Remember that a set will form a group under multiplication if it is associative with respect to multiplication, right? There is an identity element, okay? In this case, identity not 0, and then it will have a multiplicative inverse, then it will form a group. Okay, so without a 0, we can have a multiplicative inverse. So you can describe a division ring, right? Apart from the fact that it's an abelian group with regards to addition, with regards to multiplication, if you remove 0, it forms a group under multiplication, all right? So that's what it means. Okay, now the reason for calling such a ring a division ring is because then we can easily divide by the elements, okay? So remember we said in one of our lectures that if you have, let me pull up, if you have, if I have A, for instance, let me clear this, clear, okay. So if I have A times B is equal to A times C, okay? In general, I cannot say that this does not generally imply that B is equal to C, okay? I cannot say that this is always equal to this. I can only say this if I know that A here has a multiplicative inverse, okay? And if A is coming from a division ring, it's an element of a division ring, I know that if it is not 0, then it has a multiplicative inverse. And therefore, I can multiply by the inverse, multiply by AB, and do the same thing on this side, right? AC, okay? And then they cancel out, and I have B is equal to C. So I can do this if I know that A has a multiplicative inverse. That is if A, B, and C are non-zero, right? I can do this if I know that A has a multiplicative inverse. So if I know that I'm dealing with a division ring, then every non-zero element has a multiplicative inverse, or every non-zero element is a unit. And therefore, I could divide, all right? And then I'll get things like that. That is why it's called a division ring, okay? Okay, so that is you should keep that in mind. Great. Let's move on to let me see. Right. Okay. I'll probably end it here, and then the next lecture will continue with fields. Okay. So these definitions will become important in defining what a field is. So keep this in mind. So the next lecture will continue from here. Okay, I'll continue the next video from this place.